The interstellar comet atlas just turned gold and shattered into fragments. That's what the images flooding your screen seem to show. And if it's true, we just witnessed something that shouldn't be possible. You've seen the images. They've been everywhere for the past few days. A comet radiating this warm, almost surreal golden light, its tail spreading outward like someone threw liquid sunshine across the darkness of space. And then, just when you thought that was remarkable enough, new images appeared showing the same object breaking apart, fracturing into distinct pieces, each one trailing its own stream of debris through the void. The headlines all scream the same thing: the interstellar comet atlas has shattered. If you've been paying attention to what's happening above us, you know why this matters. This isn't just any comet. This is the visitor from beyond, an object that originated somewhere else in the galaxy, travelled through interstellar space for who knows how long, and is now racing through our solar neighbourhood on a trajectory that will never bring it back. It's only the third confirmed interstellar object we've ever detected passing through our cosmic backyard. Finding one is rare enough. Watching one break apart in real time, that should be once-in-a-lifetime material. Except there's something wrong with this picture, something that doesn't quite fit. The professional observations don't match what's flooding your social media feeds. The data coming from telescopes equipped with spectrographs, the trajectory models calculated by orbital mechanics experts, the colour analysis from astronomers who've been tracking this object since summer, none of it aligns with that golden spray you keep seeing. The interstellar comet hasn't turned gold. According to the instruments pointed at it, it hasn't broken into multiple visible fragments. Instead, it's been showing a compact structure with a greenish glow, exactly what you'd expect from certain gases reacting to solar radiation. So what's actually happening here? Why are millions of people watching what appears to be a golden comet dying and calling it the interstellar visitor when the real object looks completely different? Is this a case of old images being recycled, a breakdown in how information flows from observatories to the public? Or is something more fundamental at work, something that reveals how easily spectacular events get tangled together in the race for attention? You're not imagining the confusion. It's real, it's widespread, and it's rooted in something deeper than sloppy reporting. This is a collision between two separate cosmic events that happen to overlap in time, in discovery method, and in name. Both are remarkable in their own right. Both deserve your attention. But somewhere between the observatory and your screen, they got merged into a single narrative that doesn't actually exist. Here's what we're going to do. In the next several minutes, we're going to untangle one of the strangest cases of mistaken identity in recent astronomy. We'll trace the golden comet back to its actual designation, examine why the confusion spread so rapidly, and figure out what the interstellar visitor is genuinely doing right now as it passes through our solar system. This isn't just about correcting a mix-up between two comets. It's about understanding how we consume space news in an era where virality often matters more than accuracy. If you're fascinated by unravelling cosmic mysteries like this one, hit the like button and subscribe to join us as we uncover more real stories behind the viral headlines. Because the real story is actually more interesting than the confused version. When you understand what's happening with each of these objects, when you see them clearly as separate events rather than blurred together, both become more remarkable. The golden comet that survived impossible odds and then fractured is fascinating for reasons that have nothing to do with being interstellar, and the actual visitor from beyond our solar system is doing things that don't require it to be golden or breaking apart to be extraordinary. The confusion matters because it obscures both stories. It makes it harder to appreciate what makes each comet special. It creates expectations that don't match reality, which eventually leads to disappointment or disengagement when people realize they've been watching something other than what they thought. And in some cases, it fuels conspiracy thinking, because when the official observations don't match the viral narrative, some people start wondering what's being hidden rather than questioning whether the narrative was accurate in the first place. So let's start unravelling this. Let's figure out which comet is actually doing what, and by the end, you'll know exactly which object you've been watching in those stunning images, and why distinguishing between them matters more than you might think. Drop a comment right now if you've been following the Atlas Comet story, because there's a decent chance you've been watching two different objects without realising it. And that's not your fault. The way this information has spread has made clarity nearly impossible, unless you're deep into the astronomy community and checking technical designations on every post. Stay with me. The answer isn't complicated, but it is surprising. And once you see it, you won't be able to unsee how easily these cosmic events got entangled. Let's start with what those viral images actually show, because whatever comet this is, the event itself is absolutely real, and it's visually stunning in ways that make perfect sense for why it captured so much attention. In early October, a comet made an extremely close approach to the Sun. It swung deep into the inner solar system, venturing into a region where solar radiation becomes intense enough to vaporize surface ice in minutes and strip away material that's been frozen for billions of years. Most comets that venture this close don't make it out intact. They either disintegrate completely in the solar furnace or emerge so battered and depleted that they fade from view within days. But this one survived its close pass. And when it emerged back into observable range on the far side of the Sun, astronomers working with high-resolution equipment in Italy captured something genuinely unusual. The comet wasn't just bright. It was radiating this warm, golden yellow hue that stood out immediately. Most comets show whites, greys, maybe a greenish tint when certain molecules fluoresce under sunlight. But this deep gold colour suggested something specific about what the comet was releasing. A massive outburst of dust particles, likely rich in certain minerals, reflecting sunlight in exactly the right way to create that luminous appearance. The images went viral almost instantly, and honestly, for good reason. They were beautiful. They had this cinematic quality that makes you remember why space captivates us in the first place. Here was something genuinely rare. A comet glowing like heated metal, its tail spreading out in this broad, graceful arc that photographers from multiple locations managed to capture in stunning detail. And then, just days ago, the comet did something even more dramatic. On the night of November 11th, astronomers at an observatory in northern Italy watched in real time as the comet's nucleus began to break apart. By the following night, the fragmentation was unmistakable. Where there had been one central concentration of light, there were now multiple distinct fragments separated by measurable distances. Debris filled the space between them. Images captured over consecutive nights showed the pieces spreading apart, each developing its own small tail as they continued their journey through space. This kind of breakup isn't unheard of for comets that pass extremely close to the Sun. The intense thermal stress doesn't just vaporize surface ice, it creates internal pressure as gases trapped deep inside suddenly heat up and try to expand. If the nucleus has any pre-existing cracks or weak points, that pressure can literally tear the object apart from the inside. Some comets shatter into dozens of tiny fragments that vanish within hours. Others break into a handful of larger pieces that continue onward as independent objects, each essentially becoming its own small comet. The fragmentation added another layer to an already compelling story. Here was a comet that had survived what should have been a death sentence, only to fracture days later as if the damage had been accumulating internally, quietly, and finally became visible once the object moved away from the Sun's immediate influence. It felt dramatic, it felt significant, and it was thoroughly documented by reputable observatories using equipment sophisticated enough to capture fine details. So the images are legitimate. The golden colour happened. The fragmentation is real. All of it occurred exactly as shown in those viral posts. But here's where the narrative starts to split from reality in ways that matter. Because the comet in those images isn't the one most people think they're looking at. The golden glow came from dust, specifically from a massive release of dust particles during and after the comet's close solar pass. When sunlight hits dust grains of certain sizes and compositions, especially particles containing iron or other minerals, it gets reflected in ways that shift the apparent colour toward warmer tones. The sheer volume of dust, combined with the right particle distribution, created that distinctive golden appearance that made the comet so photogenic. The fragmentation revealed structural weakness that probably existed long before the solar encounter. Comet nuclei aren't solid rock. They're more like loosely bound collections of ice and debris, sometimes described as dirty snowballs, sometimes as icy dust balls. The exact structure varies, but many comets are fragile enough that the stress of a close solar pass, thermal expansion, outgassing pressure, even minor tidal forces from the Sun's gravity, can exploit existing fractures and split the nucleus apart. What you're seeing in those images is a solar system comet, one that originated somewhere in the distant outer regions where our sun's influence barely reaches, that made its way inward on a long, elliptical orbit, survived a perilous brush with our star, and then began falling apart as it moved back towards safer distances. It's a genuinely remarkable event. Professional astronomers studying it are learning valuable information about comet composition, structural integrity, and how these ancient objects respond to extreme stress. But it's not an interstellar visitor, and that distinction matters more than you might initially think. The confusion started partly because of timing. This comet was reaching peak brightness, and then fragmenting during the exact same period that the actual interstellar visitor was passing through its own closest approach to the Sun. Both objects were being actively observed. Both were generating new images almost daily. Both were subjects of excited posts in astronomy communities and on social media platforms, and both carried the same label in their names: Atlas. When you're scrolling through space news and you see stunning images of a golden comet labelled Atlas, and then you see headlines about the interstellar comet Atlas doing unusual things, your brain naturally connects them. Pattern recognition is what human minds do exceptionally well. We look for coherence, for narratives that tie information together into understandable stories. When multiple data points share similar labels and appear simultaneously, we group them together without thinking twice about it. The visual impact of the golden comet made it particularly memorable. So when people heard about the interstellar visitor and then saw those striking golden images, those images became what they pictured. They became the mental reference point for the Atlas comet. And once that association formed, contradictory information, like scientific observations showing something completely different, had trouble breaking through. This is where we need to pause and actually look at what the interstellar visitor has been doing, because it's been observable, it's been photographed extensively, and none of those observations show anything remotely like what you've been seeing in the viral gold images. Now let's shift our attention to the actual interstellar visitor, the object that genuinely deserves the designation as something from beyond our solar system, because what this comet is actually doing is unusual enough without needing to turn gold or break apart to be remarkable. This is 3I Atlas, formerly designated C2025 N1, the third confirmed interstellar traveller ever detected passing through our cosmic neighbourhood. It's following what's called a hyperbolic trajectory, a path that isn't gravitationally bound to our Sun. It came from somewhere beyond our solar system's influence. It's passing through the inner planets region right now, and it will eventually head back out into interstellar space, never to return. Its origin point is somewhere else in the Milky Way galaxy, though exactly where remains unknown. The chemistry of this comet has turned out to be genuinely unusual. Observations from some of the most sophisticated telescopes we have, including the James Webb Space Telescope and the Very Large Telescope, have revealed that this visitor is unusually rich in carbon dioxide compared to water, with traces of carbon monoxide and some molecules we don't commonly see in solar system comets. That unusual chemistry is part of what makes it scientifically valuable. It's potentially giving us a direct sample of material that formed around a different star under different conditions than the comets we're used to studying. In terms of appearance, 3I Atlas has been showing a greenish glow. That colour has been visible in multiple observations from different observers using various equipment. The green likely comes from molecules in the comet's coma, the cloud of gas surrounding the nucleus, that fluoresce when hit by solar ultraviolet radiation. The most common source of green in comets is diatomic carbon, which is just two carbon atoms bonded together. When ultraviolet light hits this molecule, it absorbs the energy and re-emits it as green light. Interestingly, spectroscopic analysis of 3I Atlas didn't initially show the expected signatures of diatomic carbon in the quantities that would explain the intensity of the green glow. That created some scientific questions. If the green isn't entirely from diatomic carbon, what else might be contributing? One possibility is cyanogen, another carbon-based molecule that can produce greenish hues. Another is that this comet contains organic molecules we haven't fully catalogued yet, compounds that behave similarly to diatomic carbon but have slightly different spectroscopic signatures. The structure of 3I Atlas appears compact, with a well-defined central nucleus surrounded by an extended coma. Observations have also detected what's called an ion tail, a stream of ionized gas being pushed away from the comet by the solar wind. This is different from a dust tail. Ion tails are typically narrower, more structured, and can point in slightly different directions than dust tails because they're being influenced by magnetic fields in the solar wind rather than just radiation pressure. Some recent images have hinted at possible jet activity, localized streams of gas erupting from specific points on the nucleus, rather than uniform outgassing from the entire surface. This kind of activity is common in comets. As the nucleus rotates and different areas face the sun, ice deposits beneath the surface heat up and suddenly vent outward, creating these directional jets. They can make the comet's brightness fluctuate, and can even slightly alter its trajectory over time through a process called outgassing thrust. But here's what 3i Atlas has not done, at least not according to any credible professional observations. It has not turned golden. It has not produced the kind of massive spreading dust tail that you've seen in those viral images, and it has not fragmented into multiple large visible pieces. The comet remains structurally intact. Unusual, yes. Its chemistry doesn't quite match the typical comets from our own Oort cloud. Behaving in ways that raise scientific questions, absolutely. But breaking apart dramatically? No, there have been viral claims suggesting otherwise. Some posts have circulated showing what appear to be asymmetric structures around the comet, multiple bright spots, or sudden changes in brightness. These have been interpreted by some as evidence of fragmentation, or even more exotic explanations. But astronomers actually studying the comet with calibrated instruments designed for this purpose have consistently reported that the nucleus appears intact. What people are sometimes seeing as multiple pieces are likely jet structures, those localized outbursts of gas creating bright regions within the coma that can appear as separate bright spots in lower resolution images. Or they're seeing the nucleus plus a disconnection event in the ion tail, where a portion of the tail gets separated by changes in the solar wind. These are normal comet behaviors that can look unusual if you're not familiar with them, but they're not fragmentation in the sense of the nucleus physically breaking into separate objects. The actual behavior of 3i Atlas has been interesting enough without embellishment. As it approached the sun through October, its activity increased dramatically, not in unusual ways, but at rates that suggested the comet was responding strongly to increasing solar radiation. The outgassing of certain molecules ramped up faster than typical for the distance it was travelling. That kind of sensitivity to solar heating tells us something about the comet's composition and structure, about how volatile its ices are and how much material lies close to the surface ready to sublimate. There was also some discussion in the astronomy community about the possibility of an antitail, an optical illusion where the comet appears to have a spike or tail pointing toward the sun rather than away from it. This happens when our viewing angle from Earth intersects the broad, flat sheet of dust particles the comet leaves behind in its orbital plane. From certain perspectives, that dust sheet can appear edging, creating the illusion of a tail extending in the wrong direction. Whether 3i Atlas has produced a visible antitail depends on viewing geometry and how much dust it's been releasing, but it's another example of how comet appearance can create visual effects that look strange if you're not expecting them. The interstellar visitor has been producing enough gas to create a visible coma and ion tail, but it hasn't been a prolific dust producer compared to some comets. That's actually part of what's kept it from being naked eye visible, despite the massive media attention. Without a large, bright dust tail to reflect sunlight, the comet remains relatively faint, visible through decent amateur telescopes under dark skies, but not the kind of spectacle that dominates the night sky like some famous comets have. And that's fine. Not every comet needs to be a visual showstopper to be scientifically invaluable. What 3i Atlas is giving us is data. Spectroscopic signatures of molecules that formed in another star system, orbital dynamics that can potentially tell us where in the galaxy it came from, activity patterns that reveal how interstellar comets behave compared to the ones that formed in our own solar system. That information is what makes this object genuinely special. So if the golden comet isn't the interstellar visitor, and the interstellar visitor hasn't turned gold or broken apart, then how did millions of people end up thinking they were watching the same object? The answer lies in something deceptively simple and frustratingly easy to overlook: the way these comets are named, and how that naming convention gets lost in translation when it reaches the general public. Here's the reveal that explains everything. The golden comet that fragmented is officially designated C2025 K1 Atlas, and that last word, Atlas, is precisely where this entire confusion originates. Both comets were discovered by the same system. the asteroid terrestrial impact. Last Alert System, ATLAS for short, is a network of robotic telescopes operating primarily in Hawaii and Chile, designed to scan the sky for near-Earth objects. Its main purpose is planetary defense, identifying asteroids or comets that might pose a collision threat to Earth. But in the process of conducting that survey, it detects all sorts of other objects, including comets passing through the outer solar system, and occasionally visitors from interstellar space. When any observatory or survey system discovers a comet, the International Astronomical Union assigns it a formal designation following a standardized system. That designation includes several components: the letter C indicating it's a comet, the year of discovery, a letter corresponding to the half-month period when it was first observed, a number showing which discovery it was during that period, and finally the name of the survey, telescope or person who found it. So C2025 K1 Atlas translates to a comet discovered in the year 2025 during the first half of May. That's what the K indicates, and it was the first comet found during that particular time window. The atlas at the end credits the survey that detected it. Meanwhile, 3i Atlas, formerly designated C2025 N1 Atlas, was discovered in early July. The N1 indicates it was found during the first half of July, and it was the first comet discovered during that period. The 3i prefix, which stands for Third Interstellar Object, was added after orbital calculations confirmed that it's following a hyperbolic trajectory, and therefore came from beyond our solar system. But in headlines, in video titles, in social media posts, most of that technical detail disappears. The year gets dropped. The specific discovery period designation vanishes. People just see Atlas Comet or Comet Atlas, and when two different objects share that label, and both are making news simultaneously, the human brain does what it's built to do. It merges them into a single entity. This isn't a failure of intelligence or attention. It's pattern recognition functioning exactly as evolution designed it. Our minds constantly look for coherence, for ways to organize information into narratives that make sense. When you encounter multiple references to Atlas Comet, accompanied by striking images and breathless updates, and they're all appearing during the same few weeks, your brain naturally assumes they're describing the same object doing different things at different times. The timing made this confusion almost inevitable. C2025 K1 reached its closest point to the Sun in early October, and began its dramatic transformation to gold around that time. The fragmentation happened in mid-November. Meanwhile, 3i Atlas was approaching and passing its own closest point to the Sun in late October. Both comets were at peak visibility and scientific interest simultaneously. Both were generating fresh images and observations daily. Both were being discussed in astronomy forums, covered in science news outlets, and shared across social platforms. If you were casually following space news, checking headlines during coffee breaks, scrolling through astronomy, posts in your feed, watching occasional YouTube videos about what's happening in the sky, you'd see a constant stream of Atlas Comet content. One day there's news about unusual chemistry, another day there are images of golden tails, then there are reports about fragmentation, then discussions about interstellar origins. Unless you were carefully noting the technical designations and checking which specific object each piece of information referred to, it would all blur together into a single ongoing story about one very active, very unusual comet. Content creators, whether intentionally or through genuine confusion, made this worse. Thumbnails are critical for video performance. A stunning image of a golden comet fragmenting into pieces is dramatically more compelling than a photograph of a faint greenish smudge, even if that faint smudge is the more scientifically remarkable object. So videos about the interstellar visitor started using images from C2025 K1. The title would reference 3i Atlas, but the visual would be the golden spray and fragments. For viewers who don't scrutinize technical details, who trust that the images in the thumbnail represent the object being discussed, this created a false mental model. The interstellar visitor became synonymous with golden color and fragmentation in their minds, even though those characteristics belong to an entirely different comet. The algorithm rewarded this mix-up. Videos that paired dramatic visuals with high-stakes titles about an interstellar visitor got more clicks. Higher click-through rates led to more recommendations. More recommendations meant more views. More views meant more creators noticed what was working and replicated the approach. Within days, the confused version of the story was everywhere. while accurately labeled content struggled to compete for attention. This created a feedback loop where correction became nearly impossible. The mixed-up narrative had emotional resonance. An ancient visitor from beyond our solar system, turning gold and shattering apart, is inherently dramatic. The accurate information that these are two separate comets, one golden and fragmenting, one green and intact, felt less exciting by comparison, even though both stories are fascinating when understood properly. There's also a psychological phenomenon called the illusory truth effect, where repeated exposure to information makes it feel more true regardless of its actual accuracy. When you've seen the Atlas comet has broken apart dozens of times across multiple sources, when you've watched several videos showing golden fragments and heard narrators describing the interstellar visitor shattering, that becomes your reality. A correction feels like revisionist history, like someone's trying to walk back what really happened, rather than clarifying what was confused from the start. So no, you weren't wrong to be confused. The confusion is legitimate, widespread, and rooted in factors that go beyond individual comprehension or attention span. It's a collision between how science names objects, with precise technical designations that convey specific information to people trained to read them, and how information spreads in attention economies that prioritize emotional impact and visual appeal over technical precision. The two comets share similar names because they were found by the same survey system. They were both active at the same time because that's when they happened to be passing through the inner solar system. And they got entangled in public perception because the mechanisms that spread information today aren't designed to preserve technical distinctions when those distinctions reduce emotional engagement. Understanding this doesn't immediately solve the problem, but it does help you see why it happened. And maybe it helps you approach the next viral space story with just slightly more skepticism, with a willingness to pause and check whether the images match the objects being described, whether the technical names line up, whether the spectacular narrative you're being offered actually corresponds to what professional astronomers are observing. Now let's dig into why these comets look so fundamentally different, because the colours aren't just aesthetic details, they're direct evidence of completely different physical processes, creating completely different visual signatures. Start with C2025 K1, the Golden Comet. When it made its extremely close approach to the Sun, the intense solar radiation caused a massive eruption of dust from its nucleus. Comets are essentially mixtures of ice and rocky material, silicate dust grains, metal-rich particles, organic compounds, all bound together with frozen water, carbon dioxide, carbon monoxide, and various other ices. Normally, as a comet gradually warms approaching the Sun, ice near the surface sublimates, transforms directly from solid to gas, and that escaping gas carries some dust particles along with it into space. But when a comet passes very close to the Sun, this process accelerates dramatically. Layers of ice that might normally take weeks or months to sublimate can disappear in hours. The dust doesn't just trickle out gradually, it explodes outward in what astronomers call an outburst. Suddenly you have enormous quantities of dust particles filling the space around the nucleus and streaming out behind it. The golden colour tells us something specific about that dust's composition and particle size. When sunlight hits dust grains, the way that light gets scattered depends partly on what the grains are made of and partly on their size relative to the wavelength of light. Fine particles rich in iron or certain other metals can scatter light in ways that preferentially reflect longer wavelengths, reds, oranges, yellows, while absorbing or scattering shorter wavelengths. The result is that warm, golden hue that made C2025 K1 so visually striking. The sheer volume of dust matters too. A relatively small amount of dust might give a comet a slightly yellowish tint. But the massive outburst that C2025 K1 experienced released so much dust that it created this broad, luminous veil extending far behind the nucleus. Multiple observers described it as one of the most impressive dust displays they'd seen from a comet in recent years. The fragmentation likely intensified this effect. When the nucleus broke apart, each fragment exposed fresh material that had been buried in the interior, ice and dust that hadn't been touched by solar radiation before. That fresh material immediately began sublimating and releasing its own dust, adding to the overall cloud of particles around the comet. Each fragment developed its own small tail as it continued moving through space, all of them contributing to this expanding debris field, all glowing with that characteristic golden tone. Now contrast this with what's happening around 3i Atlas. The green glow is an entirely different phenomenon. This is fluorescence, a process where molecules absorb high-energy, ultraviolet light from the sun and re-emit that energy as visible light at specific wavelengths. In comets, the most common source of green fluorescence is diatomic carbon, C2, which is two carbon atoms bonded together. This molecule forms in the coma when larger carbon-containing molecules get broken apart by solar ultraviolet radiation. When diatomic carbon absorbs UV light, it gets excited into a higher energy state, and when it drops back down to its normal state, it releases that energy as green light. This process is incredibly efficient at certain wavelengths, which is why even relatively small amounts of diatomic carbon can create a noticeable green glow. What made 3I Atlas scientifically interesting is that initial spectroscopic observations didn't show the expected large quantities of diatomic carbon that would fully explain the intensity of the green colour. That raised questions. If the green isn't entirely from diatomic carbon, where else might it be coming from? One possibility is cyanogen, which is CN, a carbon atom bonded to a nitrogen atom. This molecule also fluoresces in the green part of the spectrum under solar UV radiation, and it's been detected in many comets. Another possibility is that 3I Atlas contains organic molecules that we don't see as commonly in solar system comets, compounds that behave similarly to diatomic carbon in terms of how they interact with light, but have slightly different chemical structures. The unusual carbon dioxide to water ratio in this comet adds another layer. Most comets from our own solar system show a fairly consistent ratio of water ice to other volatile ices. But 3I Atlas appears to have much more carbon dioxide relative to water than typical. That unusual composition might mean it formed in a colder region, around its parent star, or under different conditions that favoured carbon dioxide over water, ice. And that unusual chemistry might also explain some of the unexpected features in its spectrum and its unusual greenish appearance. The critical difference between the two comets is this. C2025 K1's golden colour comes from solid particles, dust grains physically reflecting and scattering sunlight based on their composition and size. It's a reflection process. The colour depends on what the particles are made of and how they interact with incoming light. 3I Atlas's green colour comes from gas, molecules in the coma absorbing ultraviolet radiation and re-emitting it as visible light through fluorescence. It's an emission process. The colour depends on which specific molecules are present and which wavelengths they emit when excited by solar energy. Dust creates broad, sweeping structures, those wide, fan-shaped tails that can extend for enormous distances because dust particles continue coasting through space long after they're released. They respond to radiation pressure from sunlight, which gradually pushes them outward and backward, creating that classic curved tail shape. Gas creates more diffuse, structured features. Ion tails tend to be narrower and straighter because they're being controlled by magnetic fields in the solar wind rather than just photon pressure. The coma around the nucleus can have complex structure, depending on where active regions are located and how the nucleus is rotating. These are fundamentally different phenomena producing fundamentally different appearances. So when you see a broad golden spray, and then hear that the object is glowing green with an ion tail, those descriptions don't match. They're not describing the same physical processes. They can't both be accurate for the same object at the same time. And that's why the viral images looked immediately wrong to anyone who had been carefully following the actual observations of 3I Atlas. It wasn't just that the colours were different. It was that the entire character of the comet's appearance, the type of activity, the structure of the tails, the distribution of light around the nucleus, was describing a completely different kind of object going through completely different physical processes. Both comets are releasing material into space as they pass near the Sun, but one is primarily a dust event, solid particles creating visible structures through reflected light. The other is primarily a gas event, molecules creating visible structures through fluorescence and ionization. Understanding that distinction helps you see why they look so different and why mixing them up creates such a fundamental misunderstanding of what's actually happening. So why did one comet fracture while the other remains intact? The answer reveals something fundamental about how fragile these ancient objects actually are, and why identical journeys near the Sun can produce completely different outcomes. Comet nuclei are not solid chunks of rock. They're better described as loosely consolidated mixtures of ice and dust, sometimes with the consistency of barely compacted snow, other times more like rubble piles where individual chunks are barely held together by weak gravity and the frozen ice acting as a binding agent. The exact structure varies from comet to comet depending on where and how it formed, what it's experienced during its lifetime, and how much material it's already lost during previous approaches to the Sun if it's been here before. When a comet passes close to the Sun, it experiences multiple forms of stress simultaneously. There's thermal stress. The sunward side heats up rapidly while the interior remains frozen, creating temperature gradients steep enough to cause cracking, similar to what happens when you pour hot water into a frozen glass. There's outgassing pressure. As ice buried beneath the surface heats up and sublimates, it turns into expanding gas that has to force its way out through overlying layers, creating internal pressure that can literally push the nucleus apart from within. And then there's tidal stress, though for most comets this is relatively minor. The Sun's gravity pulls slightly harder on the side of the comet facing it compared to the far side, creating a stretching force. For a small object, this tidal force is usually negligible compared to the other stresses. But if a nucleus is already weakened by fractures, already under internal pressure from rapid outgassing, even a small additional tidal tug can be enough to widen those cracks and trigger fragmentation. C2025K1 apparently fell into the category of structurally fragile comets being subjected to extreme stress. It survived its closest pass to the Sun initially, which itself was remarkable. Many comets that venture as close as it did simply vaporize or shatter during perihelion when the thermal stress is at maximum. But C2025K1 made it through that crucible and emerged back into observable space apparently intact. The damage, however, was already done. Internal fractures invisible from the outside had widened under the combination of thermal shock and outgassing pressure. Days after perihelion, as the comet moved away from the Sun and some of the extreme heating began to subside, those weakened structures reached their breaking point. The nucleus split, not explosively like a bomb detonating, but gradually, with pieces drifting apart as their individual outgassing created slight differences in trajectory. By November 11th, the separation was visible to ground-based telescopes. Observers described being able to see multiple distinct condensations where previously there had been one. By the following night, the fragments had spread far enough apart that their separation was obvious even in moderate-resolution images. Each piece trailed its own plume of gas and dust, creating this expanding debris field, all moving along roughly parallel paths. What you're watching when you see images of C2025K1's fragmentation is essentially slow-motion disintegration. Those pieces will likely never come back together. Each fragment is now its own independent object, and over time, they'll continue to spread apart as tiny differences in their outgassing rates push them onto slightly different trajectories. Eventually, they might fragment further into smaller pieces, or they might survive as a cluster of smaller comets, all following similar orbits, at least until they either collide with something, get perturbed by planetary gravity into a different path, or make another pass close to the Sun and disintegrate further. Now consider 3I Atlas. This comet has shown no credible evidence of major fragmentation, despite viral claims suggesting otherwise. There have been posts showing what appear to be multiple bright regions around the comet, or changes in its shape, and these have been interpreted by some as proof that the nucleus is breaking apart. But that's not what professional observations indicate. What people are often seeing as multiple pieces are jet structures, those localized outbursts of gas I mentioned earlier that create bright spots within the coma. A comet nucleus is typically not uniformly covered with ice. There are active regions where ice lies close to the surface or is particularly volatile, and quiet regions where dust layers insulate the ice beneath. As the nucleus rotates and these active regions face the Sun, they produce jets, directional streams of gas and dust erupting from specific points. From a distance, especially in images that aren't perfectly resolved, multiple jets can look like multiple objects. You see several bright concentrations within the coma, and your brain interprets them as separate pieces. But they're all coming from the same intact nucleus. It's like mistaking the streams of water from a rotating sprinkler for multiple separate sprinklers. There's also the phenomenon of disconnection events in ion tails, where a section of the tail can get pinched off and separated from the rest by changes in the solar wind's magnetic field. When this happens, you temporarily have what looks like a separated chunk of the comet drifting away. But it's not part of the nucleus, it's just ionized gas that was already in the tail, now disconnected and forming its own temporary structure. Professional observatories tracking 3i Atlas with serious equipment, Hubble, Webb, large ground-based telescopes with spectroscopic capabilities, have consistently reported that the nucleus appears structurally intact. They see activity changes, brightness fluctuations, jet structures, and all the other normal behaviors you'd expect from an active comet. But they don't see the kind of fragmentation that turned C2025 K1 into multiple distinct pieces. Why has 3i Atlas remained intact when C2025 K1 broke apart? We don't know for certain without detailed information about the internal structure of both nuclei, which we can't directly observe, but there are several possibilities. 3i Atlas might be more structurally cohesive. Perhaps the ice and dust are more tightly bound together, or perhaps the nucleus is more massive with enough self-gravity to help hold it together against outgassing pressure. Or it might simply be that 3i Atlas's close approach wasn't quite as extreme. Small differences in closest approach distance can translate to significant differences in thermal stress and tidal forces. A comet that passes at one distance might survive intact while another that ventures just slightly closer shatters. There's also the matter of composition. 3i Atlas's unusual chemistry, high in carbon dioxide, different molecule ratios than typical solar system comets, might mean its ices behave differently under solar heating. Carbon dioxide ice sublimates at lower temperatures than water ice, which could mean the comet started outgassing and releasing pressure earlier in its approach, perhaps more gradually rather than building up to a catastrophic release. The key point is this: fragmentation near the Sun is common but not inevitable. Every comet is different in structure, composition, and the exact details of its trajectory. Two comets can experience similar journeys and end up with completely different outcomes, one intact, one shattered. Based on subtle differences we can't always predict beforehand. What we can say definitively is that 3i Atlas has not fragmented in the dramatic way that C2025 K1 did, despite viral claims mixing the two events together. The interstellar visitor remains intact, still releasing gas, still showing activity, still moving through our solar system as a single object rather than a cluster of debris. Now we need to talk about how this confusion didn't just happen, but spread so rapidly and became so resistant to correction. Because understanding that process reveals something important about how information flows in the attention economy we're all navigating. The algorithm doesn't care about accuracy. That's not a moral judgment, it's just a description of how recommendation systems actually function. The algorithm cares about engagement, click-through rates, watch time, likes, comments, shares. Content that generates more of these signals gets interpreted as higher quality and gets recommended more widely. Content that generates less engagement gets buried, regardless of how accurate it might be. This creates a fundamental misalignment when it comes to scientific information. A technically accurate description of two separate comets doing different things doesn't trigger the same emotional response as a single dramatic narrative about an interstellar visitor turning gold and shattering apart. The accurate version requires more cognitive effort to understand. It involves technical designations, distinction between similar-sounding names, tracking two separate storylines. The confused version is simpler, more emotionally coherent, more dramatically satisfying. Thumbnails are where this dynamic becomes most visible. You've seen them everywhere. A stunning image of a golden comet with a broad, sweeping tail, fragments visible spreading apart, text overlay screaming something like, "Interstellar visitor breaks apart," or 3i Atlas shatters near Sun. The image is real. It's C2025 K1, properly documented by legitimate observatories, but the label is wrong. The thumbnail is pairing a spectacular visual with a high-stakes narrative about a different object entirely. That combination is almost impossible not to click if you have any interest in space. It triggers curiosity. What happened to the interstellar visitor? It triggers urgency. This just occurred. I need to know now. It triggers awe. Look at how spectacular that looks. All of those are powerful psychological drivers, and when you combine them into a single thumbnail and title, you create engagement bait that few people can resist. The algorithm rewards that click regardless of whether the content accurately matches the promise. You clicked, you watched for some amount of time, maybe you left a comment expressing confusion or asking questions, all of that counts as engagement. The system interprets that signal as this content is valuable and recommends it to more people. The creator gets more views, more ad revenue, more channel growth. The cycle reinforces itself. So creators, especially those trying to grow channels or maintain audience attention in an increasingly competitive environment, quickly learn what works. Use the most visually striking image available even if it's not technically the right object. Pair it with the most attention-grabbing label possible. If that means mixing up two different comets, well, most viewers won't notice, and the ones who do will leave comments which actually boost engagement metrics anyway. This isn't necessarily malicious. Many creators are themselves confused about which comet is which. They're seeing the same mixed-up information everyone else is seeing. They're trying to keep up with rapidly developing stories while producing content quickly enough to stay relevant, and they're operating in an environment that punishes slowness and rewards speed, even if speed comes at the expense of accuracy. Once a few high-performing videos establish the pattern, other creators notice and adapt. If your competitors are using the golden fragmentation images and getting massive view counts, while your accurately labeled content struggles to reach a few thousand views, you face a choice: maintain accuracy and accept obscurity, or adopt the successful approach and accept the compromise. Most people, facing that choice while trying to make content creation financially viable, will choose success over purity. And then the confusion spreads through simple repetition. The illusory truth effect is well documented in psychology research. Repeated exposure to information makes it feel more true regardless of its actual accuracy. When you've encountered the Atlas comet has broken apart across a dozen different videos, 3 news articles and 50 social media posts, all showing the same golden fragments, that becomes your reality. That's what happened. You know it happened because you've seen it so many times from so many sources. When someone then comes along with a correction, actually, that's a different comet. The Interstellar one is still intact. It feels wrong. It feels like revisionism, like someone's trying to rewrite the narrative you've already absorbed as fact. The correction has to fight against all those accumulated exposures, and in most cases, a single correction can't overcome that weight of repetition. Social media platforms compound this through their sharing mechanisms. A post showing the golden comet with 3i Atlas shatters in the caption gets shared thousands of times because it's dramatic and visually compelling. Each share exposes it to new audiences who often don't read beyond the image and headline before hitting share themselves. A follow-up post attempting to clarify the error might get a few hundred shares at most because corrections aren't emotionally resonant. They don't trigger the same sense of wonder or urgency. They're doing cleanup work, which is never as exciting as the original spectacle. The comment sections become battlegrounds where people trying to provide accurate information find themselves drowned out by the sheer volume of engagement. For every person explaining this is C2025 K1, not the Interstellar Comet, there are 50 comments expressing amazement at the images or speculating about what it means for the alien spaceship theories. The algorithm sees all that activity and pushes the content even harder, regardless of whether the activity consists of people being accurately informed or wildly confused. This creates a situation where correction becomes nearly impossible once the confused narrative reaches saturation. The systems that spread information today aren't designed with built-in error correction mechanisms. There's no way to append accurate information to all the previous posts and videos that spread the misinformation. Each piece of content exists independently, and once it's out in the wild being shared and discussed, it becomes essentially permanent in whatever form it originally took. This isn't just about comets. This dynamic plays out across every topic where technical accuracy matters, but where simplified, emotionally resonant narratives are easier to spread. Health information gets distorted the same way. Economic data gets oversimplified into dramatic but misleading stories. Political events get flattened into narrative arcs that sacrifice complexity for emotional coherence. Understanding this doesn't immediately solve the problem. You can't personally fix how algorithms evaluate content or how platforms incentivize engagement over accuracy, but understanding the mechanism gives you tools to navigate it better. You can learn to pause when you see dramatically compelling headlines and ask whether the images actually match the object being described. You can check whether technical designations line up. You can look for sources that prioritize clarity over virality even if they're harder to find. And maybe, if enough people start doing that, if enough viewers start rewarding accuracy with their attention and engagement, the incentive structures might gradually shift. But that's a long-term cultural change, not a quick fix. For now, the system rewards confusion when confusion is more emotionally satisfying than clarity. And that's why two separate comets got merged into one impossible object that both did and didn't turn gold, that both did and didn't shatter, depending on which conflicting narrative you encountered first. So why does any of this actually matter? Why spend time untangling two comets when the universe contains countless more interesting mysteries? Because this confusion reveals something crucial about how we engage with science in an age of viral information, and the consequences extend far beyond astronomy. When spectacle replaces substance, when emotional narratives override careful observation, we don't just get the facts wrong, we lose the ability to appreciate what's genuinely remarkable about reality. 3i Atlas is legitimately extraordinary without needing embellishment. It's only the third confirmed interstellar object ever detected passing through our solar system. Think about that. Humanity has been watching the skies for thousands of years, using telescopes for centuries, and we've identified exactly 3 objects that definitively came from beyond our sun's gravitational influence. 3. That scarcity alone makes each one scientifically invaluable. The chemistry of this visitor is teaching us about conditions around other stars. When telescopes analyze the gases coming off 3e Atlas, they're sampling material that formed in a completely different stellar system under potentially different conditions than what exists in our own neighborhood. That unusual carbon dioxide to water ratio, the unexpected molecules showing up in spectroscopic analysis, these aren't just curiosities. They're clues about how planetary systems form in different galactic environments, about what kinds of ices can accumulate in different temperature and radiation conditions. Observations from Webb, Hubble, and major ground-based observatories are capturing data that will be analysed for years. The trajectory of this comet might eventually tell us approximately where in the Milky Way it originated, which could reveal information about stellar populations in that region of the galaxy. The way it responds to solar heating tells us about its structure and composition. This is not hype. This is not exaggeration. This is genuine scientific opportunity. But when people think 3i Atlas turned gold and broke apart, they're not engaging with the actual object. They're engaging with a fictional composite, a mashup of 2 different events that happen to overlap in time and naming. And that composite doesn't teach us anything useful. It doesn't help us understand interstellar comets, because the fragmentation didn't happen to the interstellar comet. It doesn't help us understand close solar encounters, because the chemistry being reported doesn't match the object that had the close encounter. Meanwhile, C2025K1 deserves its own recognition for what it actually accomplished. This is a comet from the distant reaches of our own solar system, making what's likely a once-in-its-lifetime passage through the inner planets. It survived a solar approach that should have destroyed it. It produced one of the most visually striking dust displays seen in recent years. Its fragmentation is giving astronomers real-time data about how comet nuclei respond to extreme thermal stress and what that tells us about their internal structure. That's valuable science happening right now, but it gets lost when C2025K1 is treated as just a visual prop for a different object's story. It becomes backdrop rather than subject, spectacle divorced from its actual physical context. The confusion also erodes trust in science communication more broadly. When people eventually realize they've been watching the wrong comet, when they discover that the spectacular images they've been sharing don't match the object they thought they were documenting, several things can happen, none of them good. Some people feel misled and disengage entirely, assuming that if this story was confused, probably all space news is equally unreliable. They withdraw their attention and miss out on genuine discoveries because they've lost confidence in their ability to distinguish good information from noise. Others double down on skepticism in unhelpful directions. If the observations don't match the viral narrative, maybe the observations are wrong. Maybe there's a cover-up. Maybe authorities are hiding what's really happening. This kind of thinking flourishes when there's a perceived gap between official information and popular belief. Rather than questioning whether the popular belief was accurate, some people question whether the official information is honest. And some people simply move on to the next spectacular claim, without ever processing that the previous one was confused. They accumulate a mental model of the universe that's built on stacked misconceptions. each one seeming reasonable in isolation but combining into an understanding of space that doesn't match reality. None of these outcomes serve the goal of creating a scientifically literate public that's genuinely excited about what's actually happening in space. And the tragedy is that both comets are fascinating enough on their own terms. You don't need to conflate them. You don't need to borrow drama from one to make the other interesting. Each is worth understanding individually, worth paying attention to for what it actually is rather than what a confused narrative turned it into. Here's what makes this particularly frustrating. It's okay to have been confused. The naming system is deliberately technical and opaque to non-specialists. The timing was genuinely unfortunate, with both comets active simultaneously and both generating newsworthy observations at the same time. The information environment we're all swimming in prioritizes engagement over clarity in ways that make confusion nearly inevitable for casual followers. You're not less intelligent for thinking these were the same comet. You are working with incomplete information delivered through systems that actively obscure technical distinctions when those distinctions reduce emotional impact. That's not a personal failing. That's a systemic problem. But now you know the distinction, and that knowledge gives you agency. The next time you see a headline about an Atlas comet, you can pause and check which specific designation is being referenced. You can look at the images and ask whether they match the type of activity being described for that particular object. You can choose substance over spectacle by seeking out sources that prioritize technical accuracy, even when it requires more effort to understand. Both of these comets, C2025 K1 and 3I Atlas, are worth your attention on their own merits. The golden fragmenting comet and the intact green interstellar visitor are both telling us important things about how comets work, what they're made of, how fragile they are, and what that reveals about conditions in different parts of the galaxy. You can appreciate both stories without needing to merge them into something neither one actually is. What matters now is what you do with this clarity. Do you keep spreading the confused version because it's more emotionally satisfying? Or do you start pointing out the distinction when you see others mixing up the two comets, even knowing that clarity is less likely to go viral than drama? That choice, multiplied across millions of people engaging with this story, determines whether we gradually improve how space science gets communicated or whether we keep prioritizing spectacle over truth. So let's bring this investigation to a close by clarifying exactly where things stand with both comets and what we should actually be watching for in the coming weeks. C2025 K1, the Golden Comet, has fragmented into multiple pieces that are now spreading apart as they continue their journey through the inner solar system. The fragments are still visible through telescopes, though they'll likely continue fading as they move farther from the Sun and the initial burst of activity from the breakup subsides. These pieces will pass closest to Earth in late November, coming within about 37 million miles of our planet. Not particularly close in astronomical terms, but near enough that decent, amateur equipment can still capture images if you know where to look. Whether those fragments will survive as distinct objects or break down further into smaller pieces and dust over the coming months remains to be seen. Some comet fragments from similar breakups have persisted as trackable objects for years. Others have crumbled into debris clouds that become too diffuse to observe within weeks. Time will tell which fate awaits C2025 K1's remains, but astronomers will keep watching because every bit of data helps refine our understanding of comet structure and what determines whether fragments survive or disintegrate completely. The golden colour has likely faded by now, as the massive dust release that created that striking appearance dissipates into space. What made the comet so photogenic was that temporary surge of dust during and immediately after its close solar pass. As that dust spreads out over larger and larger volumes of space, its density decreases and it becomes less effective at reflecting sunlight. The fragments themselves may now appear more like typical comets, greyish or white, maybe with a slight tint depending on their ongoing outgassing, but probably nothing like the spectacular gold that made those viral images so compelling. 3. Atlas, meanwhile, continues its path through our solar system intact and active. It passed its closest point to the Sun back in late October and is now moving outward, heading back toward the interstellar medium from which it came. It will make its closest approach to Earth in mid-December, though even at that point it will remain well over 100 million miles away, far enough that there's zero chance of collision or any direct influence on our planet. For observers, 3-Eye Atlas remains a challenging but achievable target if you have decent equipment and dark skies. It's not bright enough for naked eye visibility, and it won't become so during this passage through our solar system. But with a good telescope, something with at least a 6-inch aperture, and knowledge of where to point it, you can capture images showing the comet's greenish coma, its ion tail when conditions are right, and potentially some of the activity features that astronomers have been documenting. The scientific observation campaign will continue for months as long as the comet remains bright enough to study. Different telescopes will track it at various wavelengths, building up a comprehensive picture of its chemistry, its structure, its behavior as it moves away from solar heating and activity gradually decreases. Every observation adds to our limited knowledge of interstellar comets, objects we've only been able to study on 3 occasions in all of human history. What should you be watching for in news coverage going forward? First, check the designations. If you see C2025 K1 or just K1 Atlas, that's the fragmenting golden comet. If you see 3-Eye Atlas, C2025 N1, or references to the Interstellar Visitor, that's the intact green comet from beyond our solar system. Those technical details matter. They're the key to knowing which object is actually being discussed. Second, match the descriptions to the object. If an article talks about fragmentation or multiple pieces or breakup, that's describing C2025 K1. If it discusses unusual chemistry, interstellar origins, green glow, or trajectory calculations suggesting extrasolar origins, that's describing 3-Eye Atlas. When the description doesn't match the designation, you've found a confused or mislabeled report. Third, check the images. Golden colours and broad dust fans indicate C2025 K1. Greenish hues and narrower, more structured tails suggest 3-Eye Atlas. Multiple bright fragments clearly separated from each other. That's the solar system comet, not the interstellar one. When thumbnails and titles don't align, question which one is accurate, and finally, consider the sources. Are they distinguishing between the 2 comets carefully, or are they treating Atlas Comet as a single entity? Are they showing awareness that confusion exists and taking steps to clarify? Or are they contributing to the mix-up by using ambiguous labels and mismatched visuals? Sources that acknowledge the complexity and work to maintain clarity are the ones worth following more closely. What happens next with both comets ultimately depends on factors we can't control and in some cases can't predict. C2025 K1's fragments might produce additional outbursts if fresh ice gets exposed as they continue breaking down, or they might simply fade gradually as their surface layers get depleted. 3-Eye Atlas will continue releasing gas and dust as long as solar radiation remains intense enough to drive sublimation, but that activity will decrease as it moves outward into the colder reaches of the solar system. Eventually, probably sometime next year, both will fade below the detection threshold of most telescopes and will stop generating news. C2025 K1's fragments will continue on their elongated orbits, perhaps returning to the inner solar system again in thousands or millions of years if they survive that long. 3-Eye Atlas will escape our solar system entirely and return to interstellar space, travelling for millions or billions of years until it potentially encounters another star system, where it might provide the same kind of brief scientific opportunity it's given us. For now, we have this moment, this chance to observe both objects, to learn from them, to appreciate them for what they actually are rather than what confused narratives have turned them into. Both are genuine cosmic events worth paying attention to. Both are teaching us something about how the universe works, and both deserve to be understood correctly, as separate phenomena that happen to overlap in time but remain distinct in every way that matters. You now have the tools to track them accurately. You know which is which, why they look different, and how to spot when coverage is mixing them up. Use that knowledge, share it when you see others confused, and maybe gradually we can shift how these stories get told so that accuracy doesn't have to compete quite so hard against spectacle for attention. Because reality, when you see it clearly, is spectacular enough.